Hi all, welcome to a new video. Here we'll be discussing about the Hall effect. This is an important topic in the solid state devices. So here we'll be discussing about the theory of Hall effect with relevant equations, and we'll do a sample problem from the previous year university exam of BTech. So the statement of Hall effect goes like this. When a current carrying semiconductor is placed in a transverse magnetic field, an electric field is induced on the device in a direction perpendicular to both the current flow and magnetic field, okay, due to which a voltage can be measured across the device, which is known as the Hall voltage, and it is usually represented as VH. Now as you can see in the figure, this is the setup for demonstrating the Hall effect. A semiconductor which is biased is placed in a transverse magnetic field, due to which an electric field is induced across it, and the direction of the electric field induced can be given by the Fleming's left hand rule, which says that the electric field, the direction of current flow, and the magnetic field will be mutually perpendicular to each other. That is why the subscripts are given as X, Y and Z, denoting the three axes. Okay, so due to this electric field, the electrons will be experiencing a pull towards the electric field. That is why the electrons are shown to be accumulating to one side of the material, okay, due to which a potential difference is created across the material, and that is causing the Hall voltage, which can be measured using a multimeter. Now let us see the expression for Hall effect. First, let us see what is the magnetic force acting on the material. That can be given as Fb is equal to Q into Vd into B, where Vd is the drift velocity of the carriers and B is the magnetic field, Q is the charge. Okay, so that is given as equation 1, that is the magnetic force acting on the material. Now moving on to the electric force, it can be given as Fe is equal to Q into E. Q is the charge, E is the electric field. Electric field can also be represented in terms of voltage as E is equal to VH by D, where VH is the Hall voltage measured and D is the distance between the 2 points between which we are measuring the voltage. So Fe can be rewritten as Q into VH by D. So that is equation number 2. Now since in steady state condition the electric force is balancing the magnetic force, we can equate the two. So Q into Vd into B can be given equal to Q into VH by D. From that we get the expression for Hall voltage as VH is equal to Vd into D into B. That is the product of drift velocity and the distance between the 2 points between which we are measuring the Hall voltage, and B, that is a magnetic field. Okay, now in terms of current density we can rewrite the expression for Hall voltage. Current density is given by the expression N into Q into Vd that you have already learned in the previous lessons. So substituting that, VH can be given as J is the current density divided by NQ into D into B. Okay, now current density means it is the current measured across the area. So J can be rewritten as I by A. So substituting the values, A means the cross-sectional area, that will be equal to D into W, where D is the width of the material and W is the thickness of the material. So substituting the value of J as I by D into W, we get VH as VH is equal to B into J divided by W into Q into N. Here N is the carrier concentration. Okay. So here 1 by Qn, we substitute that as a constant known as the RH, Hall coefficient. Okay, 1 by Qn is called the Hall coefficient. So substituting for that, we get the Hall voltage as B into RH divided by W. So this is an important expression, okay, for Hall voltage. Now RH, that is the Hall coefficient. The expression for Hall coefficient is given as 1 by Qn for the N-type material and 1 by Qp for the P-type material. So as you can see, in N-type material, Q, that is the majority charge carriers, are electrons, therefore Q will be negative. So the RH coefficient, the Hall coefficient RH will also be negative in case of N-type material, and it will be positive for a P-type material. Now the expression for mobility in terms of RH is given as sigma n into RH, where sigma is the conductivity of electrons and RH is the Hall coefficient. Similarly for the P-type, it can be given as mu P is equal sigma P into RH. So these are the important mathematical expressions from the topic. We have summarized all the expressions that we have derived just now. So you have to learn all these equations to do the mathematical problems from this section, and this is a very important topic which is frequently repeated in the university exams. So make sure you by heart all these expressions. Okay, moving on to the application of Hall effect. Let us The principle of Hall effect is made use in the measurement of carrier concentration, mobility, magnetic field, conductivity, and also to determine the type of a material, whether it is N-type or P-type. These are the important applications of. Now let us discuss a problem from this topic. This question was asked in the KTU University exams in the year 2022. So let us see. So the question is, a sample of silicon is doped with 10 raised to 17 per centimeter cube of phosphorus atoms. What Hall voltage would you expect in a sample which is 100 micrometer thick and the current flow is 1 milliampere and the magnetic field is 10 raised to minus 5 Weber per centimeter square. So this can be solved by simply substituting in the given expression VH is equal to B into I divided by W into Q into N. Here B is given as 10 raised to minus 5 Weber per centimeter square. The value of I is 1 milliampere. W is given to be 100 micrometer, and you know Q is, since this is phosphorus, it is the electrons are the majority carriers, so Q will be the charge of electron 1.6 into 10 raised to minus 19 coulomb. It is actually negative in sign, but here we are asked only for the voltage. So and then N is given as 10 raised to 17. So by substituting the values, you will get the voltage to be around 6.25. So that's it. Thank you.